Why is it so difficult to enter a black hole? What distinguishes a ballerina from a black hole? Naturally, a ballerina does not symbolize the demise of a celebrity. Considering how narrow a ballerina's event horizon is, you couldn't possibly notice it. It is positioned someplace inside the dancer. The dancer might easily lose light. The most bizarre occurrences in the cosmos do not exist in the ballerina. They appear to be rather distinct, don't you think? Well, it would seem that they do share at least one thing, at least in terms of physics. The dancer goes through the identical physical process as the black hole as she begins to spin. The conservation of angular momentum is a relatively straightforward physical principle that is essentially present everywhere in the universe. We can better understand why the ballerina spins more quickly when her arms are near to her body by using the conservation law. But it also explains why falling into a black hole is so challenging. Watch this video with me to learn more about black holes, ballerinas, and other topics. I'm sorry, but the reality is that plunging into a black hole is not fun. In actuality, it is much harder than you imagine. Science fiction books and movies have traditionally described black holes as enormous gravity sources from which nothing can escape, not even light. The famed singularities, which are points in the fabric of space-time where the laws of physics fail, are regarded to be the ultimate absorbers. However, falling into a star is far simpler than falling into a black hole. Do you consider my arguments to be absurd? Now pay attention to this. Which galaxy, if there were two of them, one with stars and the other with black holes, would you believe would be the simplest for your spacecraft to navigate? It's the one with black holes, I'm telling you. Even though they are the best absorbers, their enormous sucking effect is only possible within a very narrow radius. Black holes are like pins in the space, and while they can bend it, the curvature is only truly peaking at the singularity, so as long as you remain away from it, you won't collapse. Otherwise, as long as you maintain a certain distance, you are secure. The situation is far more challenging for stars. Because a star is a sphere, the gravitational curvature it produces is considerably more widely dispersed. You should take extra care to avoid entering a star-filled galaxy if you manage to come upon one. You would have less open room to travel, which would make it more difficult to accomplish this. I believe you understand what I mean. However, there is a lot more than this. It's extremely challenging to enter these strange cosmic holes. Even Einstein thought you couldn't go inside of them. Although we cannot definitively say whether he was correct or incorrect, we do know that physics makes every effort to prevent you from entering a black hole. We have occasionally seen observed matter being expelled from black holes. However, we will address this eventually. The concept of a black hole is probably recognizable to everyone in this room. These things are extremely dense because there is so much mass packed into such a little space. The curvature of space increases infinitely. Black holes prevent you from leaving them. Bolt is unable to leave the black hole. Elon Musk might have some innovative ideas, but based on what we currently know, not even light can. You can bid the rest of the cosmos adieu once you cross a black hole's event horizon. However, this does not necessarily imply that you will stumble into it. You may possibly begin orbiting the singularity for billions of years before that occurs. Naturally, you spin more quickly as you go to the black hole, but this doesn't cause you to fall into it. Similar to how a slide steepens as you move further down it, the black hole accelerates you to relativistic speeds as you approach its center. But almost always, you won't find yourself getting close to the singularity. The conservation of momentum then comes into play at this point. But first, let's discuss the construction of a black hole in order to fully grasp this idea. In most cases, a disk of accretion surrounds the singularity. Scientists have noticed it, therefore they are aware of it. When matter is drawn in the direction of an object with a strong gravitational field, such as a star or a black hole, an accretion disk, a flattened, elliptical, or circular structure, is created. A wide range of astronomical objects are discovered to be surrounded by accretion disks, from protoplanetary disks around extremely young stars to comparatively small regions of a few thousand kilometers around white dwarfs and neutron stars. The largest accretion disks, roughly equivalent to the existence of accretion disks across a wide variety of scales and in systems that appear to be extremely different from one another, points to some shared physical principles that may underlie their development. Small rotations in any infalling material are amplified when it compresses inwards towards the star or black hole because angular momentum is always conserved. Similar to how ballerinas or ice skaters spin faster when they pull their arms inside is this movement. Please allow me to elaborate. Consider a collection of things. Physics states that the motion of such items, commonly known as their momentum, must always be constant. When we state that the momentum must be conserved, we mean this. In essence, the total momentum of the two particles must match the initial momentum of the first particle if a particle with momentum collides with a particle that is stationary and the two bounce away from one another. The same idea applies to astronauts on the International Space Station who move to maintain their balance, as well as to what happens when a rocket is ignited, its engines are fired, and it takes off. The upward and downward momentum are equal, resulting in a net zero momentum, which, incidentally, was the same you had when the rocket was standing still on the launch platform with no engines running. Once you add up the momentum imparted to the air by the propellant going down and the amount given by the rocket going up, then the upward and downward momentum are equal, resulting in a net positive momentum. But what does this have to do with accretion disks and black holes? Black holes do not actually require accretion disks to exist. Simple black holes are real, according to science, but they are only discovered there, unhappy and lonely. They only have a mass, a spin, and an electric charge, thus they are not difficult. Black holes vary in their level of curiosity, though. For instance, a star may begin to break apart if it is discovered close to a black hole due to the black hole's gravitational attraction. Material from the star begins to spiral around the black hole over the course of 1 million years, getting sucked in and forming an accretion disk. It can take the black hole between 101 billion years to completely engulf this accretion disk. The matter first condenses into a flat ring around the black hole's event horizon before that. And because of momentum conservation, it does not sink in. We discuss angular momentum in this situation since the disk is rotating. We'll use a ballerina as an illustration. The dancer is rotating on one point while her arms are extended. What would occur if the dancer suddenly tucked her arms into their bodies? She'll naturally begin spinning much more quickly. This is so because the ballerina's hands are moving with angular motion. The momentum in the hands is moving at a specific pace when the arms are extended, and when the dancer tucks her arms, the momentum is still attempting to maintain that speed but is now moving over a much shorter path. The ballerina rotates quicker since it is moving at the same speed. This is a well-known illustration from literature illustrating the conservation of angular momentum. The beauty of physics is that its conclusions are quite universal and may be applied to both small and large-scale phenomena. A black hole's surroundings are captured in its gravitational pull and are orbiting in the accretion disk. Due to the fact that angular momentum is always conserved, as a substance approaches the center, its speed increases and it begins to move in an ever smaller orbit at the same speed as the ballerina. When matter spirals toward the center of a black hole, this is what occurs. You must thus picture this material, which was taken from another star and spiraled into the black hole at relativistic speeds, being drawn in. At some time, the material in the accretion disk meets its speed limit. Due to the restriction set by the speed of light, it has encountered a roadblock. The stuff surrounding the event horizon is heated at this level by collisions and friction. Everything gets quite warm. You shouldn't go because you would burn to death in the oven. Temperatures of up to 10 million Kelvin are possible. According to Einstein's famous law, E equals mc squared, when this occurs, atoms collide, and these collisions force them to give off more and more of the atom's mass, turning that mass into energy. According to scientists, between 10 and 40% of an atom's mass is released in the form of energy in this way. This energy output causes the accretion disk to seem to be extremely brilliant. Yet how much brighter can it get? Please rate the video before moving on in order for us to continue to improve and make these movies better for you, the viewer. Additionally, be sure to click the bell to subscribe to the channel so that you don't miss any of our weekly videos. Quasars, the brightest of these disks, can shine more than 1 billion times brighter than all of the stars in the Milky Way galaxy put together. Even more intriguing, though, is the fact that a small percentage of supermassive black holes, the enormous ones known as quasars that lurk at the centers of galaxies, emit light-speed jets of particles as they munch. However, they believe that the interaction of a black hole and the accretion disk is what gives jets their power. Astronomers are unsure of what causes jets to exist. The most widely accepted theory for the formation of jets is that the charged particles in the fast-spinning accretion disk will generate a strong magnetic field that will be in close proximity to the black hole. The field is wound into a tight cone at the black hole's rotational poles if the black hole is spinning because of the drag it causes. This twisted field is what accelerates particles away from the black hole as jets and, in doing so, takes energy away from the black hole's rotation. In conclusion, physicists believe that falling into a black hole is both feasible and difficult. But there are other options as well. It's also possible to avoid falling into them. There are numerous ways a black hole could end your life. The heat produced while spiraling in the accretion disk would probably kill you. If you reached the singularity, you might become spaghetti-like. Or perhaps you could be injected into space as a component of a plasma jet traveling at relativistic speeds. In any event, I advise against approaching a black hole. Here's where the video ends. What do you make of it? Tell us in the comments section below. Please remember to share the video if you liked it, and I'll see you again on the channel soon.